Hello, everyone. Thank you for joining. My name is Tobias Ternström, and I run product management for Amazon Aurora.
Hello, everyone. I'm Murali. I run the engineering for Aurora. Thanks for coming. Let's start. OK, so we'll start with just explaining what Aurora is. A quick recap of database internals, nothing too deep, just to motivate why we built Aurora. Cloud-native database architecture, and how we achieve durability at scale, some performance results, and some of the features and examples with global databases, fast database cloning, and backtrack. Tobias.
Oh, sure. So what is Amazon Aurora? Well, it's a database that gives you the speed and availability of commercial databases, but with the simplicity and cost-effectiveness of open source database. It's compatible with MySQL as well as PostgreSQL, and it has an easy pay-as-you-go pricing model across both compute and storage.
OK, thank you. So just to do a quick recap, I chose B plus trees because it's widely used in the database. So just to explain a few concepts. So the data within the B plus tree is organized in fixed set of pages. For example, in Aurora MySQL, we use 16 kilobytes of pages. And that is kept in memory, and we refer to that as buffer pool. And this is how the database maintains the memory state. And periodically, it's serialized into data pages on durable storage, and that is called as checkpoint. So essentially, each page in memory is persisted durably, so that when you have a cold restart or you want to take it from backup, there is data there. And when you think about how database operates on these data pages, the data is actually modified in place. So you have a page in memory, it is modified in place, and there is a standard protocol, which we refer to as do, redo, undo protocol. And the log records that are generated with before and after images are stored in a write-ahead log. So let's take an example. So you have an old state. This is a page. And then we do an operation. You get a new state. And the before and after images that is stored in log records in val. When you want to redo this operation, you take the old state, you have the log record, which contains the operation that was done, and you get the new state. There may be cases where you want to do undo, in which case you take the new state, you have the log record, you have the previous state there, and you do the undo operation, and you get the old state. So let's see how this is done for a crash recovery.
OK, so let's take an example here. So in the middle column here, you can follow pages that are written to disk. And on the right-hand side, you'll see the pages that are written to the transaction log. And we're starting here with one transaction, and time moves down. So the one transaction is run, and it has committed. Now we've made the change in the buffer pool in memory, as well as written it to the transaction log. And we'll get to that, why we need this undo-redo protocol. Next, we have a transaction T2 that has started while the transaction was run. And as soon as this transaction ran, it updated in the buffer pool, and it's generated the log record and written that durably to storage. Now, while this transaction was running, the database did this checkpoint procedure that Murali mentioned. So the checkpoint basically means anything that has been updated or changed in memory since the last time I since the last time I did the checkpoint, I'll write to disk. And the thought here is that when you restart, you have to get the database to a consistent place, and then you can basically only need to worry about things that happened after the checkpoint. So in this case, the checkpoint happened. This blue page that we wrote in transaction 1, it's been written durably to the data files of the database, whereas transaction 2 wasn't because it wasn't committed yet. Okay, so that's only in the transaction log. Then we have transaction 3 that runs. It's written to the log and updated in the buffer pool. And then we have transaction 4 that started, but it never got to commit because we had a system failure. Okay? So whatever it managed to do while it was running is in the transaction log, but there's no commit record, if you will, in the transaction log. So now the system restarts, and what does it need to do? Well, transaction 1 it doesn't need to worry about because that was written to the data files when checkpoint occurred, so it can ignore that. Transaction 2 was started but was never committed, so it needs to redo transaction 2 based on what was written durably in the log so that everything is consistent. Transaction 3, it needs to redo the whole thing because nothing was updated before the checkpoint. And transaction 4, it needs to undo because transaction 4 never committed. So this is where you can kind of see the redo undo protocol in action. So a recap on the IOs required to actually manage persistence. So again, we have the same type of columns with the durable storage for the data files as well as the transaction log. So when you write, there is going to be one IO that's writing to the transaction log. If many things happen at the same time, sometimes these IOs can be combined across transactions. But one IO for that, even if it's only a few bytes, you need to write that, because otherwise you can't guarantee durability, you can't redo, right? Then you need to do a page protection write. So I call this suspenders and belt write. Because of the fact that we're writing a 16K block, you could manage only to write some of it when the crash happens. So we need to make sure that it actually is fully written. So you write it once into a scratch pad space, if you will, and then you write it again when the checkpoint happens. So now we have actually 3 IOs. It's kind of the minimal, if you will, to write to a traditional relational database. And as you can see here, IOs probably matter quite a bit for performance, especially when it comes to writes to databases. Merli did this slide, so it says databases are all about I/O. There might be some other stuff that databases do also, but mostly about I/O.
What about the UX on top of it?
Yeah, there is UX on top of the I/O, this query optimization, processing, stuff like that.
Right. Thank you. So let's talk about, the key motivation, as Tobias mentioned, is the database does a lot of I/O. So this is what the traditional database architecture look like. You have a compute instance which processes the SQL statements, it does transactions, it does caching, what we showed as buffer pool, and then there is logging which goes into the storage system, and there is attached storage. And because it does a lot of I/O, the best idea we had so far is increase the I/O bandwidth or decrease the number of IOs. This is all we could do, right? In Aurora, we took a slightly different approach. So we look at log as the database. So assume that there is a log stream from the beginning of the database time. So you have T0 to T now, you have all the log records. Any version of a database page can be constructed using this log stream, right? So let's take an example, okay? You have a blue page at T5, and we can create that using the log records that were created at T1 and T5.
Are most pages blue or some?
It could be red as well.
Oh, red also.
Yes, right. So we also refer this as coalescing. Essentially bring all the log records for a particular page, put them together, create a new page image. That's what we call as coalescing, right? So the first problem, right? If we rely only on the log stream for page reads, it's not practical. It's going to be too slow.
Why is that slow?
Because if you have the log stream from time 0, assume that you have a database that is running for a year, right? So to do any page read, you need to go from time 0. So 1 year worth of logs needs to be replayed. So that's not practical, right? So the solution here is periodic checkpoints. This is what a traditional database also does. Right?
It's like mini replays every once in a while.
Once in a while. So then, one approach we could have taken is let the database do this. This is what the traditional database was doing, and as Tobias mentioned, that's where the I/O inflation happens. For a small column update, you end up writing 32 kilobytes at a minimum, if 16 kilobytes is the page size, right? So the solution we came up with is why not offload that work to a distributed storage fleet, which does continuous checkpointing. So essentially, the Aurora method is to just write log records to the distributed storage, and the distributed storage does the continuous checkpointing. So when you do a page read, when the database does the page read, the latest version of the page is already coalesced and ready for serving. Right? So how did we achieve that? Right? So we looked at the overall stack. There is a compute, and there is a storage, and there is a clear difference between compute lifetime and the storage lifetime. Compute instances, they can fail, they can be replaced, they can be shut down to save cost, they can be scaled up, down, out, based on the load needs, right? But in case of storage, we cannot lose the data. It has to be long-lived. So the thought process is the lifetime requirements itself gives us an idea of separating compute and storage, right? So by decoupling, we can also get the scalability, availability, and durability, and we'll go through them and how Aurora achieves that. So in case of Aurora, we built this log structured distributed storage system, which is multi-tenant. That means that the storage offers the data from multiple databases on the same storage layer. It is multi-attached. That means that multiple database instances from the same database cluster can attach to the same distributed storage. And it is purpose-built for databases. By that, we mean that the storage intimately understands log records and the pages. And in case of Aurora, the storage system understands MySQL page format, Postgres page format, all the data structures, and so forth. Right? And we leveraged several services in AWS to build this. So we did not build our metadata store. We use DynamoDB for that. We use Route 53 for our naming. We use EC2 for our instances. We did not have our own custom hardware. We use instances that have local attached SSDs on it, i2s and i3s. And we use Amazon S3 for storing our backups. So let's dive deep into how I/O flows in a storage node. WS.
Thank you. So, okay, so the red square on your left there is an example of a database instance, and then this green storage node, we've zoomed into one of the storage nodes. And if you've heard, Aurora writes to 6 copies of every page or everything, it writes to 6 of those things. So 6 separate storage nodes, 2 in each availability zone. So we've zoomed into one of them. And then the other green box you see under the red one there is other buddies of this one, so other friendly nodes or peer storage nodes. So let's take a look at an actual I/O that happens. And the first thing that's interesting, so here we send log records over. The first thing that's a little bit magical with Aurora is when do you send the log records? So in a traditional database, when do you send it? You would think that you send it as soon as you kind of finished creating the log record. Well, that's not practical because, as we mentioned before, as soon as you generate a log record and if you write it, you use an I/O. And you can only do so many I/Os per second depending on your storage subsystem. So you want to group them, like you want multiple log records to come together somewhere, and then you write them in batches. So you typically have some sort of log buffer that buffers up until you have enough writes or there's enough delay in the system that it goes, okay, fine, I'll write this to the log now. And obviously, once you have a commit, it will have to wait until the durability, until it has been written, until it says, okay, I've done with the commit. With Aurora, we don't do I/Os to disk anymore. We do network I/O. We send it from the database instance over to the storage node, and that's a lot cheaper. So we'll still do some buffering, but you can have a much smaller network buffer, if you will, until it gets sent over to the storage node, which means you can move faster. Okay? So we send it over to the storage node. Now, in fact, we send it then to all 6 storage nodes at the same time. So we've zoomed into one of them. So it comes into the storage node, into memory, into a buffer on the storage node. The first thing that storage node then needs to do is it needs to write it to disk. So we know that we didn't lose this log record, okay? So it writes it to disk. We call it this hot log here. And then it can say, okay, I've got it back to the database instance. And the database instance then only needs to track what's going on with its 6 reads. And it can actually continue moving forward. The only time it actually needs to wait is when it issues a commit. Then it needs to wait for at least 4 of these folks to have written all of the log records. Okay? So, and this is the only thing that's synchronous in the communication. So as soon as it's been written to the disk on the storage node, it continues. Okay? So the next steps are all asynchronous, if you will. The database instance doesn't have to wait for them. So next step after this is creating these pages, so this optimization that Merle mentioned earlier, so that we don't have to reconstruct all of the pages all of the time from the beginning of time. So it does this with using this update log. And obviously, I can't create a page until I know that I have all log records that have been generated up until a certain point in time, right? There can't be any holes in the chain, because then the redo protocol doesn't work and I get the wrong page. So it will wait until it has enough of these pages there. Now, it will also do this gossiping. So what happens if I'm missing a log record? So I have 5, but I'm missing 4, and I have 1, 2, 3. Well, then I can go ask my buddies, my other peer nodes, hey, this log record 4, do you have that? And in fact, the storage node speaks Spanish, so it's like, hola, ¿qué tal? It gets it. We're working on Swedish. It's way more complex. So then it gets its log records. Once it has the full sequence, it coalesces and generates the page and writes it to disk. So now we have the pages, and this is kind of our internal checkpoint, if you will. And then, as time moves on, we ship those data pages over to S3, as well as the log records. So I can use S3 then for point-in-time recovery to any point in time. And then, obviously, we generate these pages all the time, so not having the page is a problem for performance because you have to redo everything. Having too many of the pages is obviously a waste. So once we know that the pages aren't needed anymore, we can go and garbage collect them. Okay? We can never garbage collect log records. Those we have to keep, right? Because you may need them for a point-in-time recovery. And then we periodically also do a checksum validation to make sure that there wasn't a problem with a page. And if we find a problem with the page, it can go speak Spanish again to its friendly peers to get that page from them. So again, only the first 2 steps are actually synchronous, so something that the database instance waits for. The rest are asynchronous. And again, it sends it to 6 of these storage nodes, so all of this happens in parallel in 6 different locations, or more, but it's for each page, if you will, it's 6 different locations.
Okay, thank you. Thank you, Tobias. So we looked at a single storage node. So let's look at how we achieve scale. So at scale, there is going to be some failure in the fleet at any given point. There's going to be failing nodes, failing disks, failing switches, and so forth. So how do we handle that? Right? So the Strawman solution for this is do replication. So a typical idea is let's use 3 availability zones. Let's put 1 copy per availability zone. Then do write and read quorum of 2 out of 3. It's a fair idea. Let's see if it works for all the failure cases. What about the AZ failure? Right? So still there are 2 out of 3 copies because each AZ contained 1 copy. There are 2 more availability zones that are up. So you have 2 out of 3 copies. You can establish quorum. There's no data loss. Right? What about AZ plus 1 failure? What do we mean by AZ plus 1? Now, losing a node in any given AZ is possible at any given point in time. So if you have a AZ down and a node is down as well in some other AZ, what would happen? Essentially, you lose 2 out of 3 copies. That means that you lose the quorum, you lose the data. So how does Aurora deal with that? So we replicate 6 ways. Tobias mentioned it briefly. So we have 3 availability zones that we use for any database cluster. We put 2 copies per availability zones, and we use write quorums of 4 out of 6. So let's go through the same example. What happens if a AZ fails? We still have 4 out of 6 copies. There are 2 availability zones that are up still, each having 2 copies. So we have 4 out of 6. We maintain availability. What happens if there is an AZ plus 1 failure? Right? We still have 3 copies. It's not writable, but there's no data loss.
Why can't we write?
Because we need 4 out of 6.
Why do we do that?
The reason why we need 4 out of 6 is because when we look at it's a long answer, okay? So the first part is why do we need the 2 copies? We addressed it already, because there is always one node that is failing. So, and 4 out of 6 works well to hide the tail latencies as well. So when you have this large fleet of storage nodes, there's always this SSD that is bare leveled and so forth. You can hide the tail latencies if you wait only for 4 out of 6. So in this particular case, we have lost 3 copies, and we can reconstruct the remaining copy from the remaining peers. There's no data loss, and we recover write availability. So the question then is, if you have 6 copies, okay, do you have to, how do we get the largest database size possible? We support 64 terabytes now, so you cannot obviously put 64 terabytes in a single SSD. So we use segmented storage. We partition the volume into n fixed segments.
Could we support more than 64 terabytes?
Yes, architecturally it's possible, and we are working on increasing the size as well, right? So once you partition it to n fixed segments, each segment is replicated 6 ways. So now the question is, how big should these segments be? Right? If it is too small, you're just going to have too many of these segments, so the failures are more likely. If you have it too big, the repairs are going to become long. So we experimented quite a bit, and then we settled with 10 GB as a size, and we can replicate a 10 GB segment within a minute. Right? So how do we do repairs? So let's go through that. So we use quorum sets and epochs to do repair. There is an example I can walk you through. So let's assume that there is a 6-way replicated segment on machines A to F, and all nodes are healthy. And this A to F, this quorum is available to the database node. So database manages all these metadata as well, in terms of knowing that this production group has 6 copies, and this is where they are located. So when the log records need to be sent to a particular page, it figures out which segment it belongs to, it knows all its peers, and the peers are given by this quorum. So it sends to A to F, and everything is good. It runs the 4 out of 6 quorum protocol. Right? So we do monitoring of all these storage nodes, and with pings, with instance health checks, and so forth, and we might find that machine F is in suspect state. It may or may not be working. In which case, we create another quorum for the same replication group by adding a machine G. So now we created 2 quorum sets, one with A to F, that is the previous one, and the future quorum set, which contains F replaced with G. So in this particular state, there are 7 nodes in that production group. And the database instance now writes to both of these quorum sets and waits for 4 out of 6 from both of them. So essentially, if F is up in terms of database view, it is actually writing to 7 nodes instead of 6. Okay. This is good because we can always abandon one of the quorums at any given point. We are not losing any data. Right? After some point, the system can determine that F is actually not healthy and it can be removed, in which case we can drop the first quorum. And we have cleanly moved on to adding a new node into the replication set.
So we're being kind of proactive to make sure that we don't have to rebuild a node when it's acute.
Correct. So this Aurora is continuously self-healing, and this is a procedure that we use for hard failures if a machine is down or SSD is broken or there is any network problem. All of that goes to the same process. It's a single approach we use, and this is also used for continuous heat management. So when you do placement of these segments across these thousands of SSDs, depending on the workload of the database, you might have some database which is heavily used, in which case you will have, because of the multi-tenancy, you might have impacts, in which case we move segments out to provide more I/O bandwidth, more space, and so forth. So whether it is hard failure or soft failure or maintenance operation, everything goes through the same process here. Tobias, you want to talk about the performance?
Oh, yes. So let's take a look at I/O profile and just contrast little bit what we've talked about, Aurora versus traditional MySQL. Most databases work roughly like this. So you have here MySQL with a replica, and all of these arrows that point in different directions here have different colors that you can see at the bottom. So for example, you can see that the transaction log or the log records or log writes are the blue ones. The bin log used for replication traditionally are the red arrows. Then actual data replication is the gray one. Yellow is this suspenders and belt writes, or double writes, we call them here. That must be something wrong. And then the metadata files. So essentially, you can see that we're writing from the replica. We're sending all of these I/O over to the secondary. And then on both sides, we're writing both to data files and to data files in a primary storage unit, and then we're sending it also to a secondary storage unit if the storage unit fails. So there's quite a lot of I/Os here. So in the I/O profile here for a 30-minute sysbench run, there was 780,000 transactions, and you can see here average 7.4 I/Os for each transaction. So the number of I/Os would be 780,000 times 7.4. Now, if you look on the Aurora side, you'll see that the colors differ quite a bit. So the only thing that goes from the writable replica to the read replicas, as well as to the storage nodes, are log records. So we send the log records, like we said before, to the 6 storage nodes so that they can run through this protocol that we saw. We need to send them also to the read replicas because the read replicas have their own buffer pools. And if something changes, we need to update the buffer pool. But all these folks need to update the buffer pool is the log records. So you can see the only thing that's written is the log records. And then you can see here, if you look closely, on the writes to Amazon S3, we have both the log records, the blue arrow, and then we also write the gray records or the data pages. And these are the checkpoints to be able to recover fast in terms of point-in-time recovery. And so here you can see the example of the same 30-minute sysbench run on the same database instance size, if you will, where you have instead 27 million transactions and 0.95 I/Os per transaction, which makes sense. Each transaction needs to do on average an I/O for the log record. And you can imagine that this makes quite a bit of difference when it comes to performance, especially on the write side. So we say that Aurora MySQL is about 5 times faster than traditional MySQL database. Well, if you split this into writes and reads, on the left side you see the graph for writes, where the blue bars are the throughput of Aurora, and the write bars are the throughput of traditional MySQL. You can see it's actually way more than 5 times faster, which makes total sense because the other one is writing about 7 to 8 times more. So it would make sense for it to be roughly 7 to 8 times more work and 7 to 8 times more latency and 7 to 8 times less throughput. And then on the read side, you can see that the difference isn't as great, but we're still quite a bit faster because of the fact that we've optimized parts of MySQL in Aurora to handle the read throughput.
Right. So the one thing I'll add is, when the storage system scales and performs, the database also has to keep up with that. And what we had to do for Aurora is to also change quite a bit of invasive changes into the database engine. We produced a new lock manager. We changed the way we do threading, how we manage the work queues, and so forth, so that we can take advantage of the changes that we have made in the distributed storage.
The storage is too good.
Yes.
I wonder what Merli worked mostly on.
Okay, let's talk about global databases. So for global databases, we built this thing called as physical replication. Essentially, we take the log records and we ship it to a different region, and I'll explain it here. So in this particular case, primary database instance is sending the log records to storage nodes, which to achieve the 4 out of 6 quorum, and it is sending to its peers, the read replicas within the database cluster, and it's also sending it to the replication server, which then takes it and sends it to a different region, to the replication agent there, And the replication agent now behaves as a writer. And it sends to the replica instances and also to the storage. So essentially, we are getting a pipeline of log records that are flowing between regions, and we are achieving the durability in both the regions. So 2 different Aurora DB clusters, and both of them are behaving as if the writers are writing locally.
Do we send the log records in order over to the other side?
Yes.
And do you send them in serial or?
So we use multiple connections. WAN communication is very different than LAN communication. We are making sure that the log records are in sequence, but we are sending it in parallel, reassembling them, and so forth. So all the goodness that you expect from an enterprise database, we had to do. And as you see the small arrow, in case there is a break in network communication, the storage is capturing all the log records so that if the database is down, for example, or you're restarting, or network is down, we are not able to send the log records over immediately. We have it stored in the storage node, and the replication server can pull it from the storage and send it. So how does this perform? So here, because the replication server is just behaving like yet another read replica within the database cluster, it's able to keep up. So we're able to, in this example, the workload is able to keep up with 150,000 writes per second without much performance impact. It's basically the replication server is just yet another replica within the DB cluster. Low replica lag within less than a second, you can do the replication. And fast recovery, less than a minute to accept read-write workload on the region if there is a failure. So this part is same as existing Aurora logic. We didn't have to change anything here. So if you restart Aurora database cluster, the recovery happens in parallel because the storage helps in recovering it. So instead of the database pulling all the log records and doing redo and undo, we are able to distribute that work over the fleet of the storage node. So when you have to fail over to a new region, we're able to recover quickly because Aurora recovers quickly regardless of global database or not.
And it's a fully managed solution, so you don't have to manage like a replication server and a replication agent. That's just hidden from you. All you say is, I want to replicate from this region to this other region.
That's right, very good point. So let's look at how it performs. So on the left graph, on the left scale is basically queries per second, and the right scale is the lag. The right graph is the physical replication, left is the logical replication. In this particular case, we used MySQL binlog replication, the logical replication. And you can see that once you reach around 30,000 QPS, the lag shoots up. So it's not able to keep up. So this is one of the things that we see in non-synthetic workloads as well. Right? The binlog protocol is very heavy, so it doesn't scale. So you see in the global databases, so the queries QPS can go till 200,000. The lag continues to remain low, so it's below a second. And recently we also launched ability to add multiple mirrors, up to 5 mirrors. So previously you could add only 1 mirror. Now you can add multiple mirrors. And we also launched the ability to promote any Aurora database cluster, Aurora MySQL cluster, into a global database. So if you have existing database, you can make it global database. Let's look at a quick walkthrough. So here we have the primary region, which is US West, and the primary instance is writing. It's continuously inserting data. And US East is, we use it for reads. Okay, so the data is flowing between these two regions continuously. And let's see how the lag is. So essentially, the insert is happening on the left. You can see the timestamp. And at the same time, we are doing a read. And the database level, this is not the CloudWatch metric that the system shows. This is within the database you can see in your schema. that the replica lag is around 110 milliseconds. So typically, we see across many regions, the pairs, it is less than a second. So this feature is quite useful if you have a distributed application where you want read scalability. You can get this. You can use it for disaster recovery, because once you have the data flowing to a different region, you get the continuous backup and restore as well. So you can take snapshots, you can recover, and so forth. So even if you don't use global database to start creating a failover and so forth, you can use it for disaster recovery. And you can fan out your other tasks, read tasks that you might have outside a region. Let's look at database cloning. Tobias.
Yes, and I might add on, there is a big difference in Aurora in the fact that we can do all of these things in parallel. So if you remember that lots of those steps with the Spanish speaking went through, after the two, right, when we've written it durably, the database instance can continue, right? And you had this smaller network buffer, so it means we can send things faster. And then all of the system works like this. So each of the nodes can continuously just sending these log records and keep coalescing and keep looking for holes. And as soon as it doesn't have holes, it can create the pages. So because of the fact that the system works like this, you can do this at massive scale, so in parallel. And that's really the biggest difference is there's low latency for the log records to be created and sent to storage from the database instance. And in the database instances, we can move in parallel. And this applies both to the local replication as well as the global replication. And that's why you can run this massive scale with low replica lag. So database cloning, what's that? Well, it's roughly what it sounds like. I can have a database that's readable and writable, and I can say, please give me a clone of this database right now. It's pretty fast. You have a clone available, and that's both readable and writable. So there's two benefits here. One is that it's fast to create this clone, and the other benefit is that the clone now shares storage with the primary, as long as that storage hasn't diverged. So if I have, let's say, 100 gigabyte or 64 terabyte database and I clone it, I now have the clone which has access to all of this information, but it just points to the same pages in storage that the master did, or the original database, if you will, that you cloned. And because of this also, the only storage that you pay for on the clone side is whatever diverged. So obviously now if you start writing on the clone, well, we need to keep track of what changed. And those pages you'll pay for on the storage side. But as long as they're not diverging, you only pay for what you actually used. You created the 64 terabytes, and then you're paying for 64 terabytes, even though you have two fully readable, writable instances leveraging this with minimal or no performance impact. And you can use this for many things. It might be that you want to do something risky, right? You do want to practice first and just create a clone, run through it, see what happens. You may want to run just tests, create a clone, or you may want to clone because you have a template database that you created that has a bunch of gigabytes or terabytes, and you want to use that as the basis for a new database. Well, that works fine. You have the template database, you create a clone, and you run from the clone. So all of these are kind of valid use cases here.
And you can do it across account as well.
So, across accounts as well?
Yeah. So if you have a production account and you have a test account, you don't want to use the production account for your testing. So you can cross-account clone.
But then you have to pay on both sides.
No, the storage still references.
Oh, you still only pay one. This is very good. So let's see how this looks, how this works in the real world here. So we have a source database. It has, you can see here, the blue pages 1 through 4, and then we just created a clone. It has the same pages because nothing changed. So on the storage side, if you will, here we apparently have two protection groups, and again, a protection group is a set of 6 storage nodes, right? There are 6 segments right into 6 different storage nodes. And apparently page 1 and 3 is on the first protection group, and page 2 and 4 are on the second protection group. And then let's see what happens when it diverges. So now we make some changes on the source database. So now apparently we poked at page 2 here. So now it's another version of that page, if you will. And we apparently also created page 5. So you can see page 1 and 5 are now available, as well as page 2. And the other versions are also available. So now when we look at the clone database, it can also diverge. And again, here you only pay them for the union of the two, right? So the source plus whatever diversion you did on the source and the secondary. So let's just walk through an example here. So here we have a database. We ran a bunch of transactions to load it. So we have about 40 million rows. I still don't know why it's about 40 million. So there's 4 rows missing from 40 million here. Next time we should get this to 40 million even. That'd be great. And it used about 25 gigabytes of space here. So you can see the CloudWatch metric here went up to 25 gigabytes. So I go and I click in the console, I click the database and say I would like to create a clone. So now I get a clone, and you can see the top here, we're querying the clone to see that it has almost 40 million rows. Now, when we worked on this, we made sure that this was small enough so you couldn't see, but we're being honest here, it's not exactly 40 million. It's 39,000,096. But when I look at the CloudWatch metrics for the clone, we can see that the only space that's being used on the clone is about 100 megabytes. Okay? So then, let's go and update about 10 million rows again. Not exactly 10 million, almost 10 million. I think it was slightly above this time, so that compensates kind of for the 4 rows that were missing before. And now you can see, because of the fact that we diverged in the replica, then the replica now needs to store a little bit more information, so now it's 1.2 gigabytes instead of 100 megabytes. So Murli, tell us a bit about backtrack.
Right. So let me also add a couple of things about the clone. So when we create the clones, we reference the segments of the parent database, and then we create a new segment, and we make it resident on the same SSD. So when you look at the database cluster, you can create unlimited amount of clones. So you take a database, you can create a clone after clone after clone, and so forth. There is no limits on the number of clones you do. But technically, on the back end, we cannot place all those segments on the same SSD, and we transparently handle it. So we look at the utilization of the number of segments, the space utilization, and so forth, and we diverge and move it to different SSDs so that we can spread the load. So from the DB cluster perspective, we can create unlimited clones, and the storage system handles it, regardless of the number of clones you create. Let's look at database backtrack. So backtrack is a feature that we shipped that is a heavily storage-dependent feature where you can quickly bring the database to a particular point in time without having to restore from backups. So this happens when you, for example, unintentionally dropped a table, deleted a bunch of rows, and so forth in your production database. The previous approach typically people would use is to do point-in-time recovery. In this particular case, with backtrack, you can rewind the database. And you can do it multiple times. And every time you rewind, that database is also writable. So you can continue writing. For example, in this particular case, the database moved till time T1. And when it reached T2, you decide that it is not the state that you really want. So you want to rewind to T1. So what has happened here is log records have been generated, and the page versions have been generated, and so forth, till T2. So the storage knows the log record sequence numbers and the versions that have been created and so forth. But then when the customer asks, go rewind it back to T1, we make the log records and the page versions between T1 and T2 invisible. So we essentially create a tree of LSN space. Okay. And then we reach T2, the time moves forward, you reach time T3. And when you reach T4, the customer asks to rewind the database again to T3. The same thing happens. So essentially we hide the log records. Essentially you can see a tree of log records that have been formed. And you can always jump back into this invisible zone in which case we are essentially jumping into a branch of the LSN tree. And then we can show the database as of that point. And all of this operation happens in parallel. So if you have a 64 terabyte database, there's thousands of segments that are backtracked in parallel, and the database is brought into a consistent state, and you can start writing.
How far back can I backtrack?
Right, good question. So the customer has an option to set the time interval. So you can configure backtrack time interval, and today we support till 72 hours of backtrack, and you can backtrack to within that period of time. Right.
So when would I use this?
So you can use it on a disaster case, or there are cases where, if you want to iterate on a schema change. So you want to make a massive change to your database. So in your production, you don't want to do it immediately. So the typical approach is you take a clone of your production database, and then you make a schema change, see whether it works well for you. If you don't like it, you just go back in time, make another change, and so forth. The backtrack is very quick. It happens less than 10 seconds, regardless of the size of the database. So you should be able to go back and forth.
So I can clone, and then I go backtracking back and forth.
You can do back and forth. Let's do an example here. So in this particular case, there is a table with approximately 10,000 rows. But in this particular case, it's exactly 10,000 rows.
Ooh.
Okay. And we are
But just because you're talking, I promised you if it was me, this is like 10,002.
10,000. Okay. So we are looking at the descending top five rows and the timestamp at 7:05. Okay, this is the current state. Then we modified the schema. We added a new column, C1. We're not showing that in the output. We show only the C, but we added the statement is right there. We added two rows. 100,001 and 100,002 is the value for the column.
It would have been too easy if we showed the column there.
Right.
Also.
Yeah. So, this is a geeky demo. Right?
Yeah.
So then you realize that this is not a state that you want to be. Okay. So what do? So we go to the console. There's also APIs for this. For simplicity, I'm showing the console here. You can select the database cluster, backtrack, put in the time, 7:06. And in a few seconds, you get back the good old state.
So I can backtrack schema changes, drop tables, create inserts.
Yeah, you can do. As long as the backtrack window is configured correctly, you can go back and forth.
Is there a backtrack on by default or something, or do I have to turn it on?
Today, you have to turn it on. And you have to configure the hours that you want. And the same technology you see in terms of, we talked about how we store the log records, how we store the different page versions and so forth. That is exactly the same technology that we are using for accomplishing backtrack. It's just that we're not garbage collecting the log records and the page versions. We retain them as long as the backtrack window is available.
So backtrack impacts your bill a little bit.
Correct. So based on your backtrack window, you would be charged for the storage that is incurred for giving that functionality. So backtrack, internally, we talked about copy on write clone. We use a technology called as copy on write, where page versions are maintained. When a new version is being produced, we reference count, decrement the previous reference count, create a new version, and so forth. And that is the same technology that we are using for backtrack as well. So internally, if a page doesn't change on the storage node, it's just, multiple copies are not retained across the LSN tree, if you will. References. We wrote a couple of papers, Sigmod papers. I highly recommend you guys looking into it. And many of this material is explained in greater depth there. How we do persistence, how we do commits, distributed recovery, and so forth. And that's it.
Thank you.
Thank you.